Okay, welcome back. In the last video, actually, we have seen the HCP crystal structure, and before that, we have seen the crystal structure of simple cubic FCC and VCC. And here, the density. In this current video, we will see the density computation in metals. Okay, so you can expect some kind of problems from this section. That's why I'm taking it here. So the density in the metals, okay, can be calculated using these equations. Na by Vc into A, where N is the number of atoms associated with each cell, unit cell. A is the atomic weight, and Vc is the volume of the unit cell, and Na is its Avogadro, which we have discussed. So here, let us see a problem, and we can solve this one. A copper has an atomic radius of 0.128 nanometer. That means 1 nanometer is 10 raised to minus 9 meters. Please keep it in mind. And 1 angstrom is 10 raised to minus 10 meter, or 1.28 angstrom. An FCC crystal structure and an atomic weight of 63.5 gram per mole. Okay, we need to compute its theoretical density and compare the answer with the measured density. Okay, the measured density, this is the taken from the experimental value, it's 8.94 gram per centimeter. Okay, we want to calculate the compute the theoretical density. So this is the solution for this one. So this equation we will substitute N is the 4 atoms. We know that for FCC structures, it is 4 atoms, 4 and unit cell, and this atomic weight is 63.5 gram per mole. We'll put that one, and this volume VC, VC if you know that it's the volume of this unit cell, and the volume is calculated using the previous equation which is taken from our theoretical classes, which we know. And we for this thing actually we need that R, that's the atomic radius, is equal to 0.128 nanometer. It is converted here to centimeter. If you have any doubt, just revise our previous section which deals with the volume of FCC cell. You can see how it is calculated. And here this is the Avogadro stuff. So totally the value, the calculated theoretical density is 8.8. So here the measured density is 8.94. So the difference you can write it here. So that's how we will find. So as an assignment, this is the assignment which I'm planning to give, and the solution is also here in this. You search this particular link, you will get the solution for all these things. But I recommend you not to check this one. First, you try to solve it yourself, and if you have any doubts, you can refer this. So now moving to the next, this is the ceramic crystal structure. So you know that we have studied about the ceramic structures. It's more complex than that of metals. Here the atomic bond in these materials ranges purely from ionic and to totally covalent, because some are ionic ceramic crystals are there, and some covalent structures. And many ceramic exhibit a combination of these two bond types, and we can express it as a degree of some characters like ionic character or a degree of covalent character. And all that depends on the electronegativities of the atom. I think we have discussed this thing earlier, but just please have a look of this. These all are ceramic materials, and this represent the percentage of ionic characters which lies in this. So the ceramic material, what to say, materials for which the atomic bond is predominantly ionic. The crystal structure may be of us being composed of electrically charged atoms instead of Okay. Here, we are totally changing the concept of atoms in this ceramics. We are replacing it with electrically charged ions. Okay. So while discussing or while uh, while going deep into the structures of the ceramic material, don't think about atoms. Just imagine it as ions, ionic level. So the metallic ions, or the we will call it as a cation. Okay, it's a positively charged particles, or the particles, and because why it is called as positively charged particles, because they give one valence electron to the non-metallic ions or anions. Okay, since it receives a negative charge, negatively charged. So the factors affecting the crystal structure of a ceramics are like these two. First one is the magnitude of the electric charge on each of the component ions. How much charge is there for each ions? Okay. Stronger the charge, magnitude of the charge, or higher the magnitude of the charge, stronger will be the bond strength. Okay. The crystals must be electrically neutral. That means if you take the full crystal, it is electrically neutral. That is, all the cation positive charges must be balanced by an equal number of anion negative charges. So the relative size of the cation and anion is another factor which we will see in the next slide. The size of ionic radii of the cations and anions Rc and Ra. We will represent it as Rc for the size of cation and Ra for the radius of the anion. The stable ceramic crystal structures form when those anions surrounding a cation are all in contact with that cation. That means the contact is very much essential. This thing, it is better. I think it is better to explain with the help of a figure. Okay, you can see here. So you can see these things. Here there is a contact. Here there is a contact. Here there is no contact. This represent anion. This one is anion, and this one is open circle represent anion, and the colored circles denote the cation or the positive charges. Here you can see that here contact is there. So this cation keeps all these anion together, binds. Whereas here also it will binds together. But here there is no contact because the size does not permit it to come in contact. So this structure is somewhat unstable, and this structure is more stable. So the coordination number, there's a number of anion near neighbors of the cation, can call it the coordination number. So is the related to the cation anion radius, cation anion radius ratio. We can explain it in this terms.